Good morning, good afternoon. My name is Ronald Dickstaal from Eneco. I will give a short presentation about the ambitions of Eneco in sustainability and our role in the project ATES Amsterdam West. First, I'd like to introduce Eneco, our mission, and then focus on our role in the energy supplying building ATES Amsterdam West. I'll tell you something about the energy concept with ATES and solar panels. Eneco is determined to bring the energy requirement and energy consumption within the boundaries of one planet. This is called our One Planet concept. We are on the road to climate neutrality in 2035. To reach that goal in 2035, we have three important subjects: radical electrification, phasing out natural gas, and accelerating sustainable heat. For radical electrification, we invest in new wind and solar farms and mobility. Phasing out natural gas means that we are closing our gas-fired power stations for example, our district heating, and accelerating sustainable heat through innovation and investment in sustainable sources such as geothermal, aquathermal, like ATES in ATES Amsterdam West, green gas and green hydrogen. The building ATES Amsterdam West is located in Amsterdam at the district Sloterdijk, near the highways A5 and A10. The building is built in 1972. ATES Technologies, a developer from Amsterdam, bought the building in 2012 and they want to transform it into a sustainable modern building. ATES and Eneco have a long history with each other in sustainable projects. My first project with ATES was the ATES at the Zuidas in Amsterdam. It is the headquarters of Deloitte and AKD in the business district in Amsterdam. The building was in 2015 chosen as the most sustainable office in the world with the highest BREEAM score, outstanding, more than 96 points. Eneco invested in an ATES and solar panels on the roof and explores the project for more than 15 years. ATES Amsterdam West is the 11th project between ATES and Eneco. ATES developed, for example, our headquarters Eneco World in Rotterdam. This building is heated with district heating and there is an ATES for heat and cold. Another example of our cooperation is the building De Rotterdam. This building at the Wilhelmina Pier in Rotterdam is heated with district heating and the cold is from Maaswaterkoeling, water from the river de Maas in Rotterdam. Our latest project is ATES Amsterdam West, but we have also projects in Eindhoven, Utrecht, and a project to come in Den Haag. The first conversations between ATES and Eneco started in 2017. ATES had several ambitions with the project. First of all, they like to transform the building in a modern, sustainable and energy supplying building. They expanded the building to 60,000 square meters and they have the ambition to become BREEAM Outstanding and, because of health reasons, WELL Platinum. The ambition of the tenants, Alliander, APG and Intertrust, was also to become an energy producing building on the plot. There were several ideas to reach that goal. Maybe we could invest in an own windmill. Maybe energy as a service, building related and outside terrain was an idea. So solar panels on the roofs, charging points, maybe Wi-Fi. In 2018 we decided to go for ATES and solar panels in an ESCO. We invested if solar roofs within 10 miles was an opportunity because of the rules of the Dutch government. The tenants would like to solve the project on the project plot. That's why ATES chose for solar carports above the parking space and on top of the parking garage. For the technicians, the ATES has 2 aquathermal storage aquifers from 2095 cubic meters. In the technical rooms are 2 water-water heat pumps, 1 air-water heat pump, and for failures there's an e-boiler from 600 kilowatt. ATES, heat pumps, outside units, and the e-boiler. The roof of ATES Amsterdam West is completely occupied with solar panels. That's why the outside unit of the heat pump is installed above the sprinkler unit outside the building. Because of the demand of sustainable energy, ATES invested several other solutions like sustainable energy from a roof within 10 kilometers around the building. As said, the tenants would like to solve the problem on the project plot. So they choose for solar carports at the parking space and on top of the parking garage. If you want more information about the project, you could listen to our podcast and see our video at www.eneco/nl/ATES Amsterdam West. Thank you for your information and have a nice day.
Anoya Saxion. Good morning, ladies and gentlemen. Thank you very much for inviting me for the fall meeting, fall conference. I'm very happy and pleased that I can join your conference online by recording my presentation. I'll now switch to my presentation and go in more detail to the aquathermal energy storage and aquathermal and ATES technology. Well, thank you again. My name is Godschalk. I'm a business developer of the high temperature storage and ATES project nationally, but also international, and a member of the management team of IF Technology. After 15 years with experience, I'm very happy that I'm now involved in the South Korean business. My contact details are below, so if you want to call me some more, if you have any questions, please let me know. I'm working at IF Technology, and IF Technology is a consultant and engineering company in shallow and deep geothermal energy solutions. So we are not a construction company, but we help our clients with the design, with the feasibility study, permitting, and also during the realization, we perform the supervision to check the quality of the drillings and installations. And we have also possibility to monitor running systems and to give advice to our clients how to optimize the use of geothermal systems. In the Netherlands, we are market leader, and I think we are also market leader in the world because we have more than 30 years experience in the field of shallow geothermal. And with about 90 experts, we can cover the whole field of everything which has to do with aquifer thermal energy storage and aquathermal. So we are working on we have realized more than 3,000 projects during the last 30 years, and we have major focus on the Netherlands, but we also have worked on projects in Belgium, in the UK, USA, Japan, China, and now we are very curious to work in South Korea. So let me first start to introduce the geothermal technologies a little bit more detail. In this picture, you see a cross section, and on the left side, you see a house with boreholes or an ATES system. So this is relatively shallow. It's often drilled to 150, 200, 250 meter, and that are normally known as the ground source heat pumps technology, the borehole thermal energy storage, or the Aquifer thermal energy storage systems. It's also possible to go a little bit more deeper, and then you go to deep depths of 300, 400, 500 meter, and that's what we call the low temperature geothermal energy. And more known is also, sorry for my telephone. More known is also the deep geothermal energy, where you go to drillings of about 3-4 kilometer depths to harvest the heat. It's good to make this distinction, and I also have another picture to show you in more detail. Is when we talk about geothermal energy, we can distinguish the shallow, mid-deep, and deep. When we look at the shallow, we have several technologies. The first is the ground source heat pump system, and the second is the borehole thermal energy storage system. And the difference between both technology is that in the orange colored technologies, you harvest heat from the soil and you use it for heating of the buildings. In the deep red colored technologies, you do not only harvest, but you also store heat or cold in the subsurface. So that's more that you use the subsurface as a battery for heat and cold instead of only abstracting heat. So you can imagine when you look at deep geothermal that it is also technology where you abstract heat from the depths to 3-4 kilometer and then use it for heating purposes or for making electricity. So the Aquifer thermal energy storage and also low temperature or high temperature ATES storage is also technology where you store heat and you can reuse it in the next season. And I think that's also important because that also gives an indication how the technology will work. Here again, the technologies. So on the left side is the closed loop system, ATES. In our setup, we often do it in that way that you store heat and cold also in the loops, because then the performance of your system is much more higher than you only use it as a ground source heat pump technology. In the second picture, you see the ATES technology. I will go in more detail in the next slides. It's also a battery where you store heat and cold. And third picture is the deep geothermal. 4 kilometers depth, you harvest the heat and then use it for heating or electricity production. And the last one is the aquathermal energy, where you use the surface water like river or lake as an energy source for charging your well system or for direct delivery to the building. Now, in more detail, here we see the picture of the aquathermal energy storage system. In this setup, you see that from the cold well, you abstract the water, and then you can have direct cooling of your building, or you can dehumidify the building, the air, and then the heat of the building will be transferred by a heat exchanger to the groundwater, and then the groundwater will be again injected in the warm well, and then you create a kind of bubble with warm water. And then during the winter time, you start to abstract from the warm water well, and you can have the heating of your building, and you re-inject the cold water back in the cold well. So in one season, you pump from cold to warm, and in the other season you pump from warm to cold. So the typical temperatures in the Netherlands is that the average temperature of the groundwater is about 12 degrees. So in this case, we just decrease and increase the temperature of the groundwater with about 5 degrees. So the cold well has a typical temperature of about 7 degrees and the warm well typical temperature of 17 degrees. 7 degrees is a perfect temperature which can be used for direct cooling of a building. So you can imagine that you only need a pump to abstract the groundwater, and then you have already your cold air. So the efficiency in cooling mode is very efficient. So coefficient of performance, COP, is often between 30 and 40. There's no other sustainable technology which has such a high performance in cooling mode. With the 17 degrees in the warm well, you can abstract, but that's not high enough for heating the building. So therefore, we use a heat pump to increase the temperature level to about 45 degrees, and then it can be used for space heating. Normally, it's combined with floor heating or with air ventilation that you condition the temperature. The technology is sometimes also used in small scale, so then with only an abstraction of a few cubes per hour, we have developed the technology to a next level where we can abstract in some cases with 250 cubes per well, which is rather a high flow rate. But of course it depends on the soil, what will be the capacity of the ATES system. Now this technology has been applied for many years, and we have now also combined it with surface water. So rivers, lakes can be used as an energy source because the solar sun, the sun is shining on the water, so the water will increase in temperature during the summer. You can harvest the heat, store it in your warm well as an this extra buffer to have enough capacity for the winter time, and the same you can do also for the cold water. When we look at the world, we see that that in the green areas there are the best options for the application of ATES. When I look at South Korea, I see that in the region of Seoul there's a lot of potential, but also maybe in Busan and more in the south western side. Typical, where is ATES applied? We see during the last years that especially for utility, which means office buildings, is a very nice technology because office buildings often need heat and cold, so that's perfect match with ATES system, but also in shopping malls, in hospitals, nearly in all buildings where heat and cold is used. Therefore, you can apply ATES. The last years we see in the Netherlands that gas is not allowed to heat our homes, so now also ATES will be applied also for residential areas. Here I just have a picture for you with some pictures of the more than 3,000 projects which we have worked on during the last 30 years. So you see the university campuses, bigger buildings. In the right corner there are also the high-rise buildings in Denmark. Hospitals are present. So in all ways we work on this type of projects. What we see in the Netherlands that when we started, of course, we were the early adapters of technology, so just a few systems has been made, but during the years you see that the growth in the amount of systems is rapidly increasing. So at the moment more than 3,000, 4,000 systems are in operation, and we still hope that we can increase this amount because it really contributes to our climate goals. Why is it so successful in the Netherlands? I think essential is that you have good aquifers because you need the ATES technology as a buffer. So you need groundwater, and groundwater is present in aquifers where you can abstract it and inject it. So in the Netherlands, nearly everywhere there are good aquifers. So that's very nice because you can tell to nearly each client that this technology can be applied. Second is that you also need a good climate because you need to heat and you need to cool. So also during the year, you need a cold period and a warm period in order to be able to store the heat and to be able to reuse it. And the last one is also that we have worked together with the several stakeholders on the legal framework. So some persons are responsible for the climate goals, some for the groundwater protection, some for the building areas. So we need to talk together to make a good framework where it is possible to apply this technology. Now, what are the golden rules for success? I think first, always start with the soil, because the soil is extremely important because you need to check what are the properties of the aquifer. So you need to do a research. Where are the aquifers? I can show you here. What are the confining layers? What are the grain size? Is it homogeneous or not? Is there any redox condition? What's the groundwater speed? So we have the luck that we have a very nice database, but if that's not possible, then there's an opportunity to use existing data or to perform a test drilling to get a better insight in the hydrogeological conditions. So that's absolutely very important. Perform with a good research to start up the investigation. Second, you should have a good integrated energy concept because the soil determines what will be the capacity for the ATES system, but you have to look at the building, how much energy is needed on the cooling side, on the heating side. Do you need to dehumidify the air? Do you need to produce tap water or not? So all these aspects need to be discussed. And we call it the SPDD-DBB approach, where you look at the source, but also at the users, the distribution. So it should be an integrated concept between what's needed and what's possible from the soil side. Then we go to the next golden rule is smart design. Which means that the basic principles are quite simple, but the way how you design the wells, what is exactly the filter size, how big are the slots, what kind of gravel do you need, that's a very critical process, which means that if you don't do it good, then you will not get a good ATES system. But we know what's important and how you can perform this. So here I also show you a picture where you can see what's the impact of the several decisions you have to make for the abstraction and injection of the groundwater. It's important that your wool system will be pressurized, that no oxygen can enter, because we often design the systems for anaerobic conditions to prevent the clogging risk. Now, the right side you see two pictures. In the top it's a clean screen, and then the second one is the polluted screen where iron precipitates has formed around the slots, the filter slots. So then you can imagine that it is very hard to inject or to abstract any groundwater from it. So that's important that you prevent the risk of clogging problems. And of course, you have to check what kind of components should you select, because we often design ATES system in salty waters, because then there's no competition with drinking water or from irrigation water or other use of the aquifers. So that's very nice, but then you need some more resistant materials to prevent corrosion. The drilling is another very essential part of the success of an ATES system. In this picture, you see a special methodology. It's not very common. We call it a reversed rotary drilling with airlifting. But the advantage of this technology is that you have a very clean way of drilling. So that means that that you use as small as possible amount of drilling fluid to prevent that the borehole wall will be contaminated, because we have a very high requirement for the well. But if you drill in a proper way and you have a proper well development, one of the pictures below, then you can see that you can use your wells for more than 50 years. There are many wells in the Netherlands already running more than 30 years without any problems and with a minimum of maintenance. So if you do it in a proper way, you have a very nice well which can be used for a long, long time. And the last is, of course, that you use the system as your friend. Which I mentioned already, it's a battery, so you need to charge enough heat and cold to reuse it for the next season. So be aware of that. We have developed a nice program so that you can monitor your system and you can control if everything works properly, and then we can also recommend how you can optimize the use of the system. Here you see another example and some monitoring requirements. Opportunity in South Korea, yes, we think there's some aquifers which can be used. We know that the South Korean government has implemented stricter measures for energy savings in buildings. So we all have the challenge to reduce the carbon footprint. So we really believe that geothermal and aquithermal solutions will help. You have some aquifers, you have rivers, you have lakes, you have good climate, so good construction sector, so all sectors are on, all traffic lights are on green, and of course you are smart entrepreneurs, so we believe that we can do a lot together. So what we can do is that we can do a capacity training. We have a lot of knowledge and experience which we are willing to share, also with other Dutch companies like Witteveen+Bos. And there are also Dutch suppliers who can provide specific materials which are necessary for the success of an ATES system. So please contact if you want to develop the business by yourself and you need some support. But the best way to be successful is not only talking about the technology, but working on projects and of course have a good dinner together. 감사합니다.
Hello, everyone. Thank you very much for inviting me for the conference and allow me to have this opportunity to present our work with regard to the ATES and aquithermal energy systems in the built environment. So if you agree for the rest of the presentation, I will share the screen. So as you see, the title of my presentation is ATES and aquithermal energy systems for decarbonizing the built environment. About myself, I'm Saleh Mohammadi. I'm a lead energy engineer at Witteveen+Bos. I have a background in building engineering. I graduated from Eindhoven University of Technology and did my PhD at Delft University of Technology in energy transition in the built environment. So I'm specialized in areas related to the renewable energy systems and sustainable building and zero energy buildings. On my role at the company, I'm a project engineer in general, but also I'm doing a lot of project management, but also beside that, doing the international business development. So this is one part of my job. Beside that, I'm also working at the university, at Saxion University, as an associate professor in sustainable building technology. And here's my contact information based my academic, but also my company emails. If you have any question with regard to this presentation, please contact me and I will be happy to help. About our company, Witteveen+Bos. Witteveen+Bos is a consultancy, an engineering firm. We provide independent consultancy services in different areas, including built environment, and infrastructure, mobility. And yeah, we have a pretty long history, I would say. We've founded in 1946 after the Second World War, and we've grown into 1,400 employees at the moment worldwide. So we have 9 offices in the Netherlands, in major cities, but also 13 offices internationally. I think here you see that we have 3 offices in the south east of Asia, in Singapore, in Indonesia, and in Vietnam, and I hope soon also in Korea. So more specifically about the energy transition and what we are doing at the Witteveen+Bos. So Witteveen+Bos is a large company, I mentioned, and which means we have a kind of expertise basically across all the energy transition spectrum and the value chain. So we can basically from early phases, from the supply side, offshore, onshore, solar, for example, bioenergy, all the way go to the demand side, for example, demand management, demand optimization, building renovations, and that sort of services, and all the kind of the renewable energy activities between these two spectrum, including the geothermal and aquathermal and ATES, which basically in this presentation I'm going to talk about. So naturally, having all this expertise means that we have a multidisciplinary approach with regard to the project. So when you are doing a project, we try to look at it from the different facets, from the different aspects, and not only focus on one specific angle. And that's also give us a priority kind of opportunity to have more kind of integrated approach with regard to the projects. And when we are talking about more specifically about the energy transition in the built environment, mainly we are talking about heating and sometimes also occasionally cooling as well. So if I want to be more specific, what we are doing in this area in Witteveen+Bos, we look at the kind of a project in different level and different scales. For example, mentioned here on the building level, we're looking basically what we could do on the buildings with regard to the designing, for example, solar energy building, or all the kind of building energy simulations that we could do for optimizing the energy use in the buildings. But we also look at the higher level and higher scales. For example, we look at the collective system, collective renewable systems for the neighborhood, for the districts, or maybe in the larger scale, in the city level, we are looking at the kind of urban energy planning, heat mappings, or heat network zoning. So this means that basically we look at the different scales across the kind of different urban levels, and we do the kind of energy and feasibility study across all these levels. So having mentioned these city scales, basically we have the thermal energy storage systems, or more specifically underground thermal energy storage systems across all these scales. So we have it both on the building, but also on the collective and also on the city levels. There's a different type of kind of underground thermal energy storage system, but here you see that the main types. I just put it here. Started from the BETIS, borehole thermal energy storage. I think it's now in Korea. ATES, which specifically in this presentation I want to discuss, and I want to talk about high temperature ATES and geothermal that, of course, interesting, but are out of the scope for this presentation. So more specifically about the ATES, ATES or Aquifer thermal energy storage. To be clear, it's a storage method. So it's a heat and cooling, kind of heating and cooling battery. And basically what's happened, if I want to very briefly mention how the system operates, is we use the subsurface, we use the aquifers in the subsurface area as a kind of battery, as a storage for storing heating and cooling over the seasons. How it works is we use the groundwater. And very simply, in the summer times, basically we extract this groundwater, and we use that as a source for our cooling system. and by extracting the cooling from the groundwater, basically that means we increase the temperature, we generate heating. So we store this kind of heated groundwater in the other well. So I forget to mention we have two wells, cold well and hot well, and they basically physically they are separated into two locations with certain kind of a distance. So when we store the heating, the heated groundwater in the warm well, in the winter basically we use that water as a source for our energy system in the building. Could be a heat pump, as a source for the heat pump basically. And by doing that, basically, we decrease the temperature and we generate cooling. So we save and we store cooling in the cold well during the winter time, and then we use it again in the summertime. So this loop can basically iterate for I think 30, 40, 50 years. And if the system basically well managed and balanced, that basically can be used for forever, because that basically, as I said, it's only work based on the principle of recovering heating and cooling over the seasons, and be as a bridge to bridge this gap between the kind of the seasons. So about the ATES system, it's an interesting technology. As you see here, there's some impressions how the systems look like. For example, in this case, this is the case that the wells and all the kind of installations are situated under the street, so below the surface of the street surface. And in this case, for example, it's partly above the kind of the surface. But the reason that I put this picture here is to see it's very it's not really significant spatially intensive. So in terms of space that you need for this technology, it's very limited. You need really not that many space for having this technology, and that makes it very easy to integrate with the in a built environment in different locations. So a little bit about this technology, with potential benefits. We have more than 3,000 running ATES system in Netherlands. So in Netherlands, it's common, this technology. It's had been used from, I think, 80 and 90. So we have a system running for 30, 35 years, and it shows that actually it's operating quite well. It's a proven technology, I would say. And in terms of the COP that the system can provide, you see is quite high, between 4 and 40, depending on the kind of season and cooling and heating modes. A lot of saving, and most of saving happening in the cooling, because in many times basically you just can use the groundwater directly as a source for cooling, so without any uplifting or downlifting the temperature. That's why we can get to the kind of 90% energy saving compared to the conventional cooling system. And in a heating mode, that could go to 50% energy saving compared to the kind of conventional heating systems. So this shows that can generate quite a significant saving for us in terms of energy. But that also led to the CO2 emission, somewhere between 40 to 90%, CO2 saving. With regard to the kind of the environmental impact on this technology, as I mentioned, basically the technology has no smell, no noise, no visual impact. Spatially is not very intensive, and has a kind of quite a positive impact on the electricity usage and heat island. So, but also that could be integrated with different type of buildings. So we have it under one building, like on a building level, for example, for one office, but also that could be applied and kind of collectively to the neighborhood and districts. So about what we do at our what we can offer as a Witteveen+Bos with regard to the ATES systems. I will not be that go into detail, just briefly mention. We can look at the kind of soil energy planning, basically in a kind of master planning wise. We look at the city, the neighborhood, where this technology could be applied, where it is suitable to have ATES system. But also in a more detailed level, we can also look at the feasibility of specific location. Does the ATES system make sense to be built in this location? We'll look at the business case. Is it financially makes sense to build this system in that location. For sure, we need to do a kind of quite a detailed geological and hydrogeological investigation of the location to see if there's enough potential to build the ATES system. But in the further steps, we can also do the kind of more conceptual and detailed design and more detailed engineering of the ATES and aquathermal energy systems. And for sure, I mentioned we are we are not looking at the ATES system only as a kind of storage, but we look at it on a kind of integral system. So this has to be integrated with the building installation, with the building energy system. So we look at the whole basically system design. We design the ATES kind of in relation to the building, and we integrate that with the buildings. And of course, we're not only bound to the designing stage, but also in the operation, we can do the kind of monitoring, but also do the kind of optimization of the ATES system itself. I will mention two reference projects with regard to the ATES and aquathermal energy systems. Two reference projects, one on the kind of more collective side. So I will look at the Floriade Expo 2022 as a kind of collective example of demonstration of this technology, but also on also on the individual building level. So I also look at the example that we did in Korea, but that was bound to only one building. So I have a kind of feeling how these systems look like, and I do two different scales. So the first example is about the Floriade Expo. I think might be some of the audience knows this expo because over the last few months we had two Korean delegation and both basically visit this project. It's one of our kind of showcase project in the Netherlands. So Floriade Expo is a horticultural world exhibition and exposition. And now it's running in Netherlands, and the goal was basically designing a sustainable, circular, and innovative expo, but also city district. And in terms of the size, you see that actually 660 homes, around 50,000 square meter utility buildings, and one special point about this expo is it will not be only expo. It will be basically after the expo period, it will be transformed to residential and the kind of urban district combined residential, but also utility building. And residential basically can increase or scale up to more than 1,200 homes. So that was the kind of specifics that has to be considered in the designing of the expo building. And the idea was basically having energy neutral district and area. So that was the ambition. Basically, was put forward by the client, and we try to reach that. So, among other things that we did with regard to the energy and energy neutrality for the expo, as part of it, we also look at the ATES and aquathermal energy system, and we designed this system as a part of the energy infrastructure of the expo. So we designed ATES system. It was basically distributed over the expo area, but also we connect the ATES system to the lake, to the adjacent lake, for the regeneration of the well. So I will not explain the regeneration. I think our partners, If Technology, has already in the presentation explained what basically the regeneration means with regard to the ATES system. So I will skip that. So we use the Weerwater Lake to regenerate the ATES system. I mentioned also here the smart thermal grid. So another innovation that we use in this expo was basically integrate the ATES and aquathermal energy system with the thermal energy storage and smart thermal grid. Basically, smart thermal grid provide a way to connect this ATES aquathermal energy system to the building, but also, regardless of this ATES system, provide the possibility to exchange energy between the buildings. Because as you see here, in the expo we have both residential but also both utility buildings, which happen in the between seasons. For example, in the fall or in spring, some of these buildings need heating, some of these buildings need cooling. For example, residential need heating, utility building needs cooling, and basically this indicate that there's a possibility to exchange energy between these buildings without storing them. So with using this smart thermal grid allow us to connect buildings directly to each other and allow the possibility of exchanging heating and cooling between them. And by doing that, also downsize the storage that we need, the seasonal storage that we need. So that was another innovative that also, for sure, that could also be applied to Korean cases as well. So this is the result. So you see here the technical room. Here you see the wells and basically the pumps and the heat pump in the technical room. And the second project that I mentioned is about Busan. It's about application of this technology on the building level. We did a feasibility study in 2020 for the Busan Eco Delta city. So as I mentioned, we only look at the feasibility of the ATES system for one building, for the smart innovation building, and we did the certain tasks, specific tasks, to see basically how feasible ATES would be for this case, including look at the kind of detailed investigation of the geological condition of the location to see if it's feasible for the ATES system. We look at the building energy demand to see how basically feasible would be to integrate the building installation with the ATES system, and basically we design a kind of integrated solution, also including the regeneration, because again, as example like Floriade Expo, we saw that there's an unbalance between heating and cooling as well in Korea. So we use basically the neighboring river water to regenerate our ATES system for the innovation building. So I will not explain this system in more detail, but I would like to present you some observations that we have seen with regard to the application of ATES and aquathermal energy in Korea compared to Netherlands. The first observation was with regard to the kind of temperature differences between the seasons. So we've seen that in Korea, unlike Netherlands, there is quite a higher seasonal temperature differences. So, and if you remember about how the ATES system works, basically this signifies that the ATES has a better operation in Korea compared to the Netherlands, because we can extract more heating and more cooling over the seasons basically to be used. So this basically favored the business case of the ATES system. It shows that it's more attractive technology basically to be applied in Korea, even than Netherlands, because of these higher seasonal temperature differences. Another observation that we saw was with regard to the hydrological condition. So there was quite similarities. For example, both Busan area and a lot of part of the Netherlands are delta environments, so they have a limited gradients, means limited groundwater flow, means more efficient ATES system. And both basically there was both fully confined layers of aquifer. So that's again that helps the operation and the business case of the ATES system. But of course there was also differences with regard to the subsoil condition. For example, the thickness of the aquifers in Korea was lower than in Netherlands. In Netherlands we have quite a thick 100 to 150 meter, but in Korea it was like somewhere between 30, 40, 50 meter aquifer thickness. and also low permeability, and also need additional test drilling and pumping tests. We observed that there is quite a lack of data with regard to the subsoil conditions. So we need more data, basically, if we want to have a more quality works with regard to the feasibility study of ATES system in Korea. Another observation, it was on the kind of more riverside, on the more hydrothermal and kind of aquathermal. We've seen that the temperature of the river water, it's compared to the Netherlands, it was like in average 5 degrees higher than what we have in Netherlands. So this is quite positive with regard both in the hydrothermal, but also with regard to the regeneration of the ATES system, because when in the summertime we have a higher temperature, basically the system can run efficiently with regard to the regeneration of the hot wells. And the last observation we've seen was with regard to the kind of the CO2 saving, CO2 emission reductions that we had compared to the reference system, which in this case was a hydrothermal. Our study shows that the ATES system can basically reduce CO2 emission by 36% compared to the hydrothermal-based system. Also, that signifies that the amount of renewables is higher than the hydrothermal system, which in this case, for example, in the case of Busan, that could goes up to more than 75% compared to the 60% for the reference system, which was hydrothermal. So this was the presentation. I hope it was interesting and useful for you. And here's my contact information. Please contact me if you have any question about the presentation or you need extra information. We would be happy to provide you. Thank you very much and have a nice day.